Okay, so today, well, I'll describe what the topology is on Galois groups after reviewing a little bit of what I did last time. I'll ask the host of this session to let me know if there are any questions. I have too much on my laptop screen right now to be looking at that. Um, so, well, actually, maybe I should start by saying, are there any questions? I see someone's asking about the slides being posted. I don't know if Alvaro, did you get my slides?
I have the slides. Were the slides for the entire? I did post slides.
Okay.
I'll figure that out. You go on.
Maybe put it in the WebEx link like you did last time.
Yeah.
And the notes, the lecture notes, I updated a bit since last time. So that's probably in the same place. So maybe just download them again if you were reading those. Okay. So, so last time we were talking about how the Galois correspondence doesn't quite work. So let me recall again. The problem is that there are basically too many subgroups. So I mentioned last time that if you look at the two power cyclotomic extensions, so these fields L sub n here, and you can go all the way to the top. Maybe I should call that L infinity perhaps, or maybe not. Let's not. Anyway, so we know what the Galois groups are at every finite level, and the problem is, for example, 5 and 13 modulo, even though 5 and 13 are different, they generate the same numbers mod 2 to the n for every n. And as exponents, they fix I, and they generate subgroups of index 2 in the units mod n. And so their fixed field has degree 2 over the base field, and well, Q adjoin I works. And Q adjoin I is fixed because 5 and 13 are 1 mod 4. And so that's it. And so we go all the way up to the top. Everything appears somewhere at some finite level. So the only things that are fixed are Q adjoin I. So we have two different subgroups that are fixing exactly, have the same fixed field. And there's nothing special about 5 and 13. If you took any odd number, B, it generates the same subgroup as 5 and 13, namely the numbers mod 2 to the n that reduce to 1 mod 4, as long as the number B is 1 mod 4 and not 1 mod 8. So in two-adic language, B would be exactly as close to 1 two-adically as 5 and 13 are. Their two-adic distance is 1/8. And so, excuse me, is 1/4. The distance from 1 is 1/4. So, yeah. And so you have lots and lots of subgroups that all have the same fixed field. And so this causes the breakdown of the Galois correspondence. And so we want to see how to fix that, how to replace all these different subgroups that generate the same subfield with kind of one correct subgroup to use instead. Okay, so if we look at the relations in the Galois correspondence, so we go from fields, subfields, intermediate fields to subgroups, and then we can go from subgroups H to their fixed fields, L to the H. And there's no problem going from a field to a subgroup back to the same field. You get back to where you started. But when you go to a subgroup to a field, the stuff it fixes, and then go back to the stuff fixing the stuff that H fixes, it could be more stuff that fixes what H fixes than just H itself. So as I write there, the field fixed by H, the automorphism is fixing it, could have more stuff than H. And so we want to figure out what that more stuff is, and we'll do that using a topology. So we'll put a topology on the Galois group that interacts very nicely with the group law, continuous operations for the topology. It's discrete for finite groups, so we never noticed it in the finite case. And it turns all the Galois groups corresponding to intermediate fields into closed subgroups. And that's the idea. We're creating closed subgroups in the Galois correspondence. And in fact, when you iterate the Galois correspondence starting from a subgroup and coming back, you get the closure of the subgroup you started with. And so if we were to start off life with closed subgroups and all intermediate fields, then we get a one-to-one correspondence. Okay, so the fields don't change, but it's the subgroups that we're using that we cut down to closed subgroups, and then we go back and forth, and everything is just as before. And we never notice it in the finite case because the topology there is discrete, and so everything is closed, and so topology is sort of pointless. Okay, so before defining what the topology is, let's let me kind of explain what the idea is. So we have some infinite extension. Maybe here's our extension, L over K, very big extension. And it's filled up by lots of finite extensions. So I'll try to use the letter F to mean a finite extension. And maybe E will just be an arbitrary extension. So we have a lot of finite extensions. And the idea of being close is that two automorphisms, if they agree on F, so let's suppose we have, well, they don't have to send F back to itself. It doesn't have to be a Galois extension. But if I were to say, for instance, that, that on here, sigma equals tau on F. So we have two automorphisms of the field L, and if they're equal on a big finite extension, we think about them as being close. It's like an analysis. You say things are closer there with an epsilon. Well, what's epsilon? Well, it depends, and the whole idea of limits is kind of quantify over all epsilon and things. At any one level, maybe it's not close enough. So you can get closer if you make F bigger. As you agree on bigger finite extensions, that's more information. You're kind of making the sigma and tau closer if you force them to agree on larger and larger finite extensions. And so that's basically the idea of the topology. We'll give it maybe a precise definition of the topology on the next slide. So let's take a look at
There is a question, Keith.
Oh, yes, question.
Actually, somebody asked, it was mentioned that a topology would be added to reduce the number of subgroups to consider. Is this similar to the idea of attaching a topology to a vector space to get a potential isomorphism with a continuous dual?
I suppose you could say in functional analysis, sure, you look at the continuous, the abstract algebraic dual space of an infinite dimensional vector space always has a bigger dimension as an abstract vector space. And so if you have a complete normed vector space and you look at the continuous linear functionals, then you get a nice relation. But let me point out, in that case, you are changing the linear functions. You're cutting down what linear functionals are of interest to you. So in this setting, there is no topology on the field. We're working with all the automorphisms of the field in the abstract automorphism sense. We're not talking about limits on the field. So it's slightly different from the functional analysis case where you put in a topology and then the continuous functionals for that topology are going to be the ones of interest where we have a nice duality theory. So in this setting, the topology is on the group of automorphisms itself. We're not going to cut down on the Galois group to say only certain automorphisms continuous for some topology on the field. So it is not quite the same thing. What would be a good analogy? Maybe I'll come back and maybe I'll think about that. And where else do we put in a topology to cut things on the functions instead of the objects they're acting on? Yeah, well, anyway, so it's not quite the same. So that actually is a good question. The topology is going to be, we're not changing the objects. The fields are the same. The automorphisms are the same. We're putting a topology, we're going to put a topology on the automorphisms themselves. So we're going to cut that down, but we're not going to remove or drop out of consideration any of the automorphisms of the field. Okay. And so as you change the finite extension on which two automorphisms agree, you're kind of changing the nature of the open sets, so to speak. So we'll see the definition of it later on, but this is the basic idea. So let's take a look at the examples that we had from before, adjoining all the square roots. And we saw that the Galois group is just using plus or minus signs on the independent square roots of -1 and the square roots of the primes. All the other square root behavior, like root 10, root 105, is all determined by what happens to the square root of the primes and square root of -1. So when we talk about automorphisms agreeing, what would it mean if I say automorphisms should agree on the subfield finite extension Q adjoin root 2, root 5, root 7? So let's write down here kind of some signs. Whoops. Hold on a second. Yeah. That's working fine. Uh-oh. Hold on a second. I'm going to switch to another stylus. Okay. Let's see how this goes. Oops. Why is it not?
I can see writing.
What?
I mean, I can see the squiggly lines that you're.
I know
writing.
those I can see. I'm just trying to. Oh gosh.
What's wrong with it?
I don't know. Okay. Anyway, I just have to put enough pressure. Okay. So all right. So if I wanted to say two elements agree on that field, then what I have to do is I have to tell you what happens on root 2, what happens on root 5, and what happens on root 7. And so that is going to, and I don't have to say anything anywhere else. It could be arbitrary. But if I put in some conditions, like it should change the sign on root 2, not change it on root 5, and change it on root 7, you give me some constraints there. Nowhere else, I don't care what happens. And the automorphisms that have that property on those three square roots, that'll cut out the idea of being kind of close as far as this finite extension is concerned. On the other hand, if I wanted to, say, look at what it means for automorphisms to be equal on Q adjoin the square root of 6, well, the square root of 6 isn't actually on this list. But you see, what happens at root 6 is determined by what happens at root 2 and root 3. Specifically, the sign changes at root 2 and root 3 have to be the same for the square root of 6 to be unchanged. And so I guess what we could say is you have to have the same sign on square root of 2 and square root of 3. And as long as you have the same sign, well, that's a condition, and you don't care what happens anywhere else. And so that's the constraint that's imposed for being equal on that field. Okay, and so that's what it means to be equal in terms of concrete formulas on the Galois group. So if you from your experience with topology, this should sound a lot like the product topology, where you put some constraints in a finite number of slots for an infinite product space, and you don't care what happens anywhere else. It's like a basic open set. So we're sort of seeing that phenomenon happening here. Now, what about for the Galois group of Q adjoin the two power roots of unity? If I tell you that I want two elements in the Galois group to be the same on the field Q adjoin zeta 8, what does that mean? And so you give me an A naught plus 2A1 plus 4A2 plus 8A3, and you give me a B So here the AIs, maybe I shouldn't use the letter I when I'm talking about two power roots of unity. Might be a possible confusion there. So AJ and BJ are zeros and ones, okay? Two adic expansions. And in fact, A naught and B naught are literally one. You can't have a two adic unit start with anything else. In any case, so what happens here is that the, as I clean up the board, to be equal on zeta 8, about the first few terms, because the higher terms are divisible by 8. And so therefore, if you think about it as a product, zeta 8 to the A naught, zeta 8 to the 2A1 to the 4A2, once you get to the 8A3, everything becomes a 1 multiplicatively, so it dies. And so if you want an zeta 8 to the B, B2. And so if you want behavior on Q adjoint zeta 8 to be the same, you need those exponents to be the same mod 8. You need A to be congruent to B mod 8, which basically means chop off everything after the 4A2 and 4B2 terms, and you're left with some ordinary numbers, and those have to be the same mod 8. In other words, another way of saying it is to say that A is the same as B mod 8, because I'm sort of writing them in base 2, it basically means all the digits have to be the same. Now, the first ones, well, those were already the same, so maybe not the best example in the world, because there wasn't really a constraint there. But that's it, okay? That's all. So that's what it means for them to look the same on Q zeta 8. The first few digits are the same. And in the same way, if you wanted these automorphisms to be equal on the subfield of 2 to the n power roots of unity, by the similar reasoning, you basically need the those exponents to be the same mod 2 to the n. In other words, you need all the digits, because they're just zeros and ones, so it's binary expansions, you need them literally to be equal from position 0 up to position n minus 1. So we did the case at n equals 3. Okay, so what we see is that being close in the cyclotomic power extension is something about initial digits being the same. And this, in fact, is exactly the same idea as in Liang's course in the p-adic metric topology. Is two p-adic numbers are in the same disk in his pictures when their initial chunks of p-adic digits agree. So we can see that this idea of automorphisms being close, when you translate it to the setting of p-power cyclotomic extensions of Q in the Galois group, it's really reflecting the same idea. So this p-adic idea comes up yet again. Okay, so that's kind of interesting. This notion of digits being close is specific to when acting on roots of unity. Okay, in a multi-quadratic example, it would look more like the product topology. So different examples might have different intuitions, but the basic idea is being the same on a finite extension, and the larger you take that finite extension, the closer intuitively the automorphisms will be. Are there any questions? I don't see any questions in the chat box. Okay, so so let's define the topology officially. So like in metric spaces, where you first have the notion of an open ball, and then a general open set is just a union of open balls. Every point in the set is inside of an open ball, which is inside of the set. So we're going to do the same idea here, but we're going to use certain subgroups instead of balls. So we'll define a basic open set and then a general open set will just be a union of the basic open sets. So the basic open set in the Galois group is around a point is just a coset cut out by a finite extension. So we have our infinite Galois extension, and the automorphisms of L that fix some finite extension, translate it by sigma, and that's an example of a basic open set around sigma. So the F here is finite. And then an open set in general is just a subset of the Galois group, so that for every automorphism in there, there's some left coset containing it that is entirely inside of that set U. Okay, and so it's very much like metric spaces, or maybe like Euclidean space, where if you know what it means an open ball around 0, open balls around everything else you just get by translation. So in some sense, the Galois groups of L over different finite extensions are basic open sets around the identity. And then we get basic open sets around other stuff just by left translating or right translating. Yeah, and so then open sets are just unions of this stuff, just like in a metric space. An open set is just an arbitrary union of open balls. Okay, so some things to note here. First of all, if you increase the field, if you go from F to a larger finite extension, well, it could be any extension, but if we're just talking about finite ones, if you increase the field, you cut down on the subgroup. Because if you fix F prime, you fix F. So when you go to a bigger field, F prime, the automorphisms that fix F prime is smaller. That's less stuff. And so the coset shrinks. And so this is the idea that as you impose a fixed condition on a bigger finite extension, you cut things down. Okay? So making F larger makes the basic open set defined by F smaller. Still, there's a natural question. What does the coset mean? I mean, it's logically, well, it's just a definition, but like, what's the content of looking at a left coset of the automorphisms fixing a subfield? It's really just saying all the stuff that looks the same on F. Okay? If you tell me that tau and F are the same thing on some finite extension, I claim that's the same as saying tau is in the coset cut out by F. Okay? Because you're telling me that for all alpha in that F, tau of alpha is equal to sigma of alpha. So therefore, let's say sigma inverse tau, the automorphisms, fixes alpha for all alpha in F. But that's exactly saying sigma inverse tau is in the subgroup fixing F. But that's exactly the same as saying tau, is in that subgroup. And these implications are all reversible. If tau is in that coset, then sigma inverse tau is inside that group, but to be in that group means that you're equal at all elements in that field. And then by applying sigma to both sides, you get back that tau and sigma had the same behavior. So the whole idea of talking about a coset cut out by a finite extension of F is just all the automorphisms that have the same behavior on a given finite extension. I'm not saying that all the automorphisms that fix F, just all the automorphisms that are equal on F. How are they elsewhere? I don't know. I don't care. But as long as you look at all the stuff equal on a finite extension, that is a basic open set in the Galois group. And a general open set is just a union of that stuff. Okay, basically you pick a bunch of finite extensions and you specify how they're supposed to behave on them, and that's well, actually, I guess that would be taking an intersection of basic open sets. We'll come to that. So a union behaves like this, or like this, or like this, and that's what an open set is supposed to look like. Okay, and by the way, if I tell you how an automorphism is supposed to behave on a finite extension, well, we know from Galois theory, or just general field theory, that a finite extension inside of a separable extension is well, it's a finite extension. So if you give me a bunch of field generators, they can only go to finitely many places. And so there's only different cosets of this subgroup Galois L over F are defined by, if you give me a bunch of field generators for F, you're just saying how they're supposed to behave on those field generators, and each of them can go to only finitely many places. So there's only a finite amount of information that can cause cosets to be different. In other words, there are only finitely many cosets. Galois group of L over F has finite index in the Galois group of L over K. So let's take a look at our examples again, and in terms of basic open sets. So if we take our Galois group of Q adjoin all the different square roots, think about the Galois group in terms of various plus and minus signs, then an example of a basic open set would be specifying, for instance, how does it behave on, for instance, Q join root 2 and Q join root 3, and not worrying about what's happening anywhere else. Or if I wanted to fix Q join the square root of 6, then we saw before, fixing Q join the square root of 6 means that the components for root 2 and root 3 have to be the same. So a basic open set in this product space amounts to fixing a finite number of square roots and then saying what the signs have to be on those square roots. Not necessarily independently, but maybe together. Like to fix the Q join root 6, the components in root 2 and root 3 have to be equal, whether they're both 1 or both minus 1, they both have to be equal, and I don't care what happens anywhere else. Independent choices. And so that's what a basic open set looks like, and it sounds like, it's just like basic opens for the product topology. An accountable product of plus or minus signs. Okay, so that's interesting. Let's look at the 5-power cyclotomic extension. So every element in this Galois group is just a collection of numbers, mod 5, 25, 125, and so forth, with a constraint. The first component cannot be 0 mod 5, and there's the congruence compatibility condition. Every number you pick at the next power of 5 had better reduce to the previous number at the previous power of 5, so that on the smaller fields, they're all compatible with each other. And so these compatible sequences, that's what that means. There was no compatibility on the previous example. If I had included in the previous example components for sign changes on the square root of 6 and the square root of 10 and the square root of 30, then I would actually have to impose constraints, like the component at root 6 has to be the product of the signs on root 2 and root 3. So I have a kind of full product in the first example only because I'm careful about only choosing independent square roots. But with the p-power cyclotomic extensions, you don't have that freedom, and you kind of have to talk about compatible sequences. And so I want to define, or I want to say that a basic open set in this case, saying how things behave, say on some 5-power finite extension, I basically need to tell you about what the exponents have to be. So for example, maybe I could say A2 has to be congruent to, I don't know, 15, 19, and 7 mod 25, something like that. Okay, so I'm just saying that now that forces constraints any elements in the Galois group for which A2 is, oh, 15, that's a terrible idea. Oh my gosh, horrible. 15 is divisible by 5. Let's say 12. Yeah, okay, let's say 12. Okay, so 7, 12, and 19 mod 25. So anything that's 12 mod 25 in the Galois group has to reduce to 2 mod 5. If you're 19 mod 25, you have to reduce to 4 mod 5. And if you're 7 mod 25, you again have to reduce to 2 mod 5. Now, I know that the 12 and the 19 are not compatible with each other, but that's okay. I'm just saying any sequence for which A2 is one of these values in the Galois group forces the value on A1, it has to be 2 or 4 or 2 for each particular sequence. But above that, it could be anything at all as long as it reduces to 12 or 19 or 7 mod 25. So what I've described here is sort of constraints that cut out a basic open set. And if you were to look from Liang's lecture at the units mod in Z5 and the 5-adic integers, this would cut out 3 balls that are kind of at the second level. He drew balls for, cutting out 5Z5 and its cosets, and then you cut down further to 25Z5 and its cosets, and this would be like 3 balls in the 5-adic integers. So that's cutting down a constraint, and that's a basic open set. And then we have our last example on this slide, and that's in the Galois group Q bar over Q, the big Galois group that is of great interest in number theory, big mysterious group. Consider all the automorphisms that fix I and, oh, look at that. I said fix I and fix the square root of 2. I really intended to make it slightly more interesting. So let me just put a minus sign here. Okay, I'll keep the I fixed. So now, are there any such automorphisms? The identity is not described, does not have this behavior. Complex conjugation does not have this behavior. Are there any elements in the Galois group Q bar Q that look like this? The answer is yes, thanks to Zorn's lemma, which lets us lift an automorphism from any finite amount of information all the way up, not in a unique way. Okay, there are a gazillion automorphisms that have this behavior, but thanks to Zorn's lemma, there are elements in the big Galois group that have any finite amount of specified behavior. And so if you look in the appendix on my course notes, you can read the proof of that. So this describes a basic open set. And so basically what this is we're looking at all the elements in the Galois group of Q bar over Q such that, on the field generated by root 2 and I, you might say fixes I and moves the square root of 2. So that's sort of a finite amount of information. I'm telling you how the automorphism has to behave on the Galois group of Q adjoint root 2 and I over Q, that little degree 4 extension. And its inverse image under everything that has that behavior all the way up on Q bar. I cannot give you a formula for such sigmas, okay, but they exist thanks to Zorn's lemma. And so this is a basic open set. If I were to further say how it has to behave on the cube root of 2 or the square root of 5 plus root 19, that's more constraints. It cuts down, but it's still a basic open set just of putting in a finite amount of information. So this description of what I'm calling basic open sets, and open sets are unions of these, this really does give a topology on the Galois group. Okay, so as you let your automorphism vary, as you slide the Galois group of L over F around, as F changes, you make it bigger or smaller, then these basic open sets, their unions do give us an actual topology. And so you should think of it somewhat like open balls in a metric space, or better yet, open balls in a Euclidean space, where all the open balls of the same radius can be obtained from 0 by translation. And so that's what we have going on here. but in Euclidean space, open balls are not a subgroup, okay? But still, so it's analogous. It's not, they're not special cases of the same thing. Well, you can always abstract things in math and make everything a special case of everything else. But anyway, it's a good analogy. You kind of define the Galois group of L over F are your basic open sets around the identity, and then you slide them around to get neighborhoods, basic open sets of other things, and unions of these are open sets in general. So so let's check the intersection property. So suppose I had a bunch of non-empty, finitely many non-empty open sets. Then if I take their intersection, well, it might be empty, not very interesting, but if you had an element sigma in the intersection of finitely many open sets, by definition, being in an open set UI means there's a basic open around sigma in UI. So it's one of these cosets, sigma Galois L over Fi. So we have our L, and then we have a whole bunch of finite extensions. And we're kind of specifying how sigma is supposed to behave on each of those. And so you have one of these cosets inside UI for each I. Now, when you have finitely many extensions, you can take the composite field, F1, F2, F3, and if you look at the Galois group of L fixing that field, well, that's going to be inside the Galois group of L fixing each of the individual Fi's. And so that one coset, that one basic open set around sigma, whoa, that one basic open set around sigma is going to be inside all of those cosets because that Galois group of L over F is inside all of the Galois group of L over Fi. And that's inside the intersection. And so you see that the intersection of opens does contain a basic open around every point inside of it. And so the intersection of finitely many open sets is open. Okay? And so this is just like in metric space topology, where you any point inside of an intersection of finitely many balls, you kind of pick the radius suitably, and you can get it inside of their intersection. Of course, open sets need not be closed under arbitrary intersections, only finitely many. Okay, so that kind of illustrates the idea that we have a genuine topology here. And an interesting aspect of this topology, it is Hausdorff. Okay, so the reason is, if you gave me two automorphisms, sigma and tau, that are different, the very definition of being different is that there's an element alpha in the big field at which they're not equal. But then if you take the finite extension cut out by that element, well, sigma and tau may not send that finite extension back to itself. Excuse me, I made a slight error there. I meant to say adjoin K. There's my finite extension. Then on that field, which may get moved around, it might not be Galois or can come back to itself, but sigma and tau are not the same function on that field because they have different values of the element alpha, which means that the coset that they both define cannot be the same coset because those cosets do not contain, they contain different element. Sigma is on the left and it's not in the right. In fact, right, the cosets are not the same because sigma and tau have different behavior somewhere on that field. But from group theory, if two cosets are different, they're in fact completely disjoint. And so in fact, these basic opens around sigma and tau are not just unequal, but in fact disjoint. But that means that we've constructed open sets around sigma and tau that are disjoint, and so the topology is Hausdorff. Okay, and so this topology on the big Galois group of L over K has the Hausdorff property. Okay? All right. If there are any questions, so let's now see with this topology that when you go from an intermediate field to a subgroup in the Galois correspondence, everything flips around. That's pretty elementary. So let's check that this group that we create from an intermediate field, arbitrary intermediate field, does not have to be finite extension. Let's check that this subgroup is closed in the Galois group. Okay? How do you show something is closed? So maybe you could try to do something with some kind of generalized limits or something. We're going to prove something is closed by showing the complement is open. Okay? So the way we'll show this is closed we're going to show that the complement is open. The complement, like the complement of any subgroup, may or may not have any structure, but we're going to show it's open because we know how do you show something is open? Pick a point in there and find a basic open inside of it that's also in there. Done. So let's assume that E is not equal to L. So we're not talking about the empty set. If we were, very easy case. Okay, so we're going to pick an element in the big Galois group that is not in the Galois group of L over E. And so what that means is there has to be something in here that is moved by alpha. Well, what we're going to do now is build a basic open set around sigma that doesn't meet the Galois group of L over E. And we're going to use alpha to do it. Take the field generated by alpha. So that's a finite extension. Okay. We can maybe put it there, or maybe better yet, put it here. Okay, so this thing comes from here. All right, so it has nothing to do with E. So we have a finite extension, and now let's think about this coset. It's an open, it's a basic open. And it's all the elements in the Galois group of L over K, in the big Galois group, that look the same as sigma. Whoops. Sorry about that. What that means then is these things do not fix alpha. But the Galois of L over E, by its very definition, fixes alpha. So that means that this coset, this basic open, does not touch the Galois of L over E at all. So this basic open is disjoint. Disjoint. The left side moves alpha, right side fixes alpha, so they have nothing in common. And so every point in the complement of this subgroup has a basic open around it that also in the complement. And so therefore the complement is open, and so this subgroup is closed. Okay. Are there any questions? Alvaro, any questions somewhere? I don't know.
Not so far.
Not so far. Okay. All right. So Now I want to show you a little bit more how the topology works. Let's see that when I take a subgroup and look at the field that fixes it, excuse me, take a subgroup, look at the field that fixes, and look at the things that fix the field fixed by H, I actually get the closure of H. Okay, and so again, this. Oops. Oh. So these are the elements, automorphisms such that tau fixes everything that H fixes. So certainly it contains H, and I want to see that in fact it's the closure of H. So we know this is closed. We just did that. We showed all subgroups of the form Galois L over something as an intermediate field is closed. And to make this the closure, so what do I want to show here? So this is closed. If I take the closure, I'm still going to be inside of there. That's just from basic topology. And so I would like equality here. Right? So what we're going to do is to show that those are equal, I'm going to pick an element. Whoops. Pick an element sigma that's in the big Galois group that's not in H bar. Okay, and I'm going to show it's not in that group either, and so therefore there's nothing in the Galois in the right side that's not in the left side. And so we know since H bar is closed, that means the complement is open, and so there has to be a basic open that's disjoint from H bar. And so this is all the things that look like sigma on F. All right. And that's disjoint from H bar. So if I pass from F to its Galois closure over K, that's only a finite extension. And making a bigger field causes the group to get smaller. We can shrink the basic open around sigma in order to put ourselves in the case where F over K is a Galois extension. Okay. And so now what you have to do is you just compare sigma on F to H on F. Right? So what we know about H by the very definition, hold on a second. So where was I?
You have about a couple minutes left, Keith.
Yeah. Right. So So what we knew is that since this is disjoint from H bar, it says nothing in H bar looks like sigma on F. Okay, different elements in H bar might not look the same as sigma in different ways. You can fill in your Tolstoy joke there if you want to. Okay, so anyway, so basically, so then if you pass to H instead, you know, H and sigma, they look different. So the bottom line is on F, sigma does not lie in the restriction of H to F. If you look at the elements of H behave on F, sigma can't look like any of that, okay? Because the very meaning of that coset being disjoint, say, from H bar. But then, what was I going to say? I lost my train of thought here. Right. So by finite Galois theory, and I'll finish up with this thought. There has to be something in F that, well, we know H on F is supposed to, there has to be an alpha such that, right, sigma alpha does, what did I want to say? Right, sigma moves it and H fixes it. Right, sigma cannot be in the subgroup defined by H. And so what that tells us then is, but since alpha was in F and, oops, right, and so alpha, what do I want to say? Right, so here we have, so alpha is in LH. And so therefore, yeah, so this whole coset, so sigma's not in the Galois group, L over LH, okay? And so what we showed then is that if you picked an element, that was not in that Galois group, then, I'm sorry, that's what we wanted to, we wanted to show that. So we picked sigma that's not in H, and then we just showed that, in fact, it's not in this group, and so therefore, so we're done. No room left. Okay, and so I'll stop there, and I'll take questions, and I'll start next time at the slides that I didn't get to today.